Greetings and welcome to Distiller. In the previous few classes, we have discussed about first law of thermodynamics. So when we talk about first law of thermodynamics, it holds for flow and non-flow processes. So when we talk about a non-flow process, then in that case, we have dq is equal to du plus dw. All right. And when we talk about flow processes, then in that case, it becomes half I'll take the entire thing, half m delta v square plus mg delta z plus delta h is equal to q minus ws. Now over here, please keep in mind that this ws that we have, this is the external work done. This is the external work done because internal work done has already been taken care of by using this delta h term. All right, the delta h terms has already taken care of the internal work done. All right, so that is why you don't need to really worry about the internal work done in this case. All right, what you actually need to focus on is the external work done, which is ws. All right, so this is ws, we call it as ws. All right, so generally it's known as shaft work, but it can also be used for certain other cases. Therefore, we call it ws. I'll refer to it as external work. All right, not simply as shaft work. All right, so in this case, this delta h is in joules, q and ws is also in joules. By chance, if you're using this law in this manner, half delta v square plus g delta z plus delta h is equal to q minus ws. So in that case, over here, this is in per kg basis. So therefore, this is going to be in joule per kg. Similarly, these two are also going to be in joule per kg. So keep that in mind while we are dealing with the first law. All right. So this is what we have discussed so far. The unit balancing also we discussed, that meter square per second square can be written as joule per kg. All right, we discussed how. Okay, so whenever we are solving problems related to first law of thermodynamics, make sure that the units that you're using, the unit balancing is very important. All right, unit balancing is very important. All right, so keep in mind that the units that you're using, when you're evaluating a particular term, then you also evaluate it, its unit side by side. All right. And one more thing, the sign convention has to be kept in mind. So heat out is negative, heat in is positive, work out is positive, and work in is negative. All right, this is the sign convention that is followed for thermodynamics. So keep this in mind as well. So with all that, we'll move on to this particular problem. The work required for compressing a gas from an initial condition of 100 kilopascal and 300 Kelvin to a final pressure of 300 kilopascal is found to be 280 kilojoule per kg of the gas. The compressed gas is admitted to a nozzle where its velocity is increased to 700 meters per second. If the gas enters the compressor with negligible velocity and leaves the nozzle at 100 kilopascal and 300 Kelvin, what is the heat removed during compression? So go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem. If you could not, then let's see how this problem is solved. The work required for compressing a gas from an initial condition of 100 kilopascal and 300 Kelvin to a final pressure of 300 kilopascal is found to be 280 kilojoule per kg of gas. So let us say that we have a compressor. Somewhere this is our compressor. All right. So in this compressor, you are having a gas that is coming in. All right. You're having a gas that is coming in. The gas is coming in at 100 kilopascal and 300 Kelvin. So this is 100 kilopascal and 300 Kelvin. All right. Then to a final pressure of 300 kilopascal. Here the pressure is increased to 300 kilopascal over here. So this is 300 kilopascal. Okay, the pressure over here is 300 kilopascal. And the work required over here is 280 kilojoule per kg. That means work input that is required is 280 kilojoule per kg. Okay, then the compressed gas is admitted to a nozzle where its velocity is increased to 700 meter per second. So over here it is admitted into a nozzle. All right, so what happens in a nozzle? It basically increases the velocity. All right, nozzle is basically there to increase the velocity of the stream, of the incoming flow rate. All right, whatever the stream is coming in, it increases the velocity and it acts like a diffuser. All right, it diffuses the entire stream very properly into the discharge. All right, when it is discharged. So we'll be dealing with nozzles further. So you'll be able to understand the principle behind nozzles very nicely. All right, for now, let's take that this is a nozzle, and inside this nozzle, and from this nozzle, velocity is increased to 700 meters. So over here, you have velocity as 700 meter per second. All right. Then they are saying that if the gas enters the compressor with negligible velocity, over here, it enters with negligible velocity. So velocity over here is 0. And leaves the nozzle at 100 kilopascal and 300 Kelvin. So at the end of the nozzle, over here, it is 100 kilopascal and 300 Kelvin. What is the heat removed during compression? So during compression, there is heat removed. So that heat removed has to be calculated by us. All right. So hope you could understand how we came to this diagram. From where did we draw this diagram? So all whatever was given in the question, we made this diagram out of it. All right. Now let's move further. Identify that where is the process starting and where is it ending. The process starts over here. We have to start from here, that the stream is entering, and we have to continue this till here where the stream is leaving. All right, so this is point number 1 and this is point number 2. All right, so over here between point 1 and 2, we are going to apply the first law of thermodynamics. All right, we are going to apply the first law of thermodynamics for flow processes. But before that, let's understand one more thing. They have given that at point 1 and at point 2, in pressure and temperature are same. This information is given so that you can identify that H1, enthalpy of 1 and enthalpy at point 2 is same. That is why the pressure and temperature are same. Enthalpy is going to be the same. H1 is equal to H2. All right, that is what we are going to take. So with all this information in our hand, we are going to apply the first law. The first law of thermodynamics is half delta V square plus G delta Z plus delta H is equal to Q minus Ws. All right. Now, the external work done is into the system, right? External work done is coming into the system. We'll mark this as equation number 1. So since it is coming into the system, therefore Ws is going to be minus W. All right, because it is going in. So this is minus 280 kilojoule per kg. All right. Then there is no difference in height as well. So we are going to get delta Z equals to 0. Hence G delta Z is also equal to 0. All right. One more thing, since over here we don't have mass, therefore delta H, Q and Ws have to be in kilojoule per kg or joule per kg. All right. Then next term is 1/2 delta V square. So that is equal to 1 by 2 into final velocity, that is 700 square, minus initial velocity, that is 0 square. So that is going to be 49 into 10 to the power 4 by 2. Okay, 49 into 10 to the power 4 by 2. This is meter square per second square, which is also joule per kg. What we need to calculate everything is kilojoule per kg. Therefore, half delta V square is going to be 49 by 2 into 10 to the power 4 into 10 to the power minus 3 kilojoule per kg. All right, kilojoule per kg. So in that case, this is going to be 245. All right, 245 kilojoule per kg. All right, this is going to be half of delta V square. All right. So we have all the, and yes, since H1 is equal to H2, therefore delta H, which is H2 minus H1, is also going to be equal to 0. So once we have all these terms, we are going to substitute in equation number 1. So when we substitute in equation number 1, we'll get 245 plus 0 plus 0 is equal to Q minus WS is minus 280. So this becomes Q plus 280. All right. So from here you'll get Q as 245 minus 280. All right. 245 minus 280. So that is going to be minus 35 kilojoule per kg. So Q is minus 35. That means heat is moving out. The negative sign implies that heat is moving out. All right, heat is moving out. So that is what we have clearly mentioned over here in the system itself. All right, Q is going out. All right, so this is how you solve problems based on first law of thermodynamics. All right, as you saw, for every term we kept in mind that we have to evaluate the unit property. So please make sure that when you are solving problems related to first law, your units are properly evaluated. All right. So once we are done with this, we move on to a very interesting topic, which is steam. All right, steam. So we are going to talk about steam, properties of steam, calculations related to steam, and all that. All right. So whenever we talk about steam, it basically is when we heat water, so we get vapor. All right, we get vapor. So this vapor form of water is your steam. All right, this vapor form of water is steam. So this process takes place keeping the pressure constant, and hence it is accompanied by a change in temperature. All right, we add heat to the water in order to increase it in order to make it into steam. So since here we usually keep the pressure constant, therefore it is accompanied by a change in temperature, right? Q is directly proportional to delta T anyways. So when you supply heat, so temperature is going to increase. All right. So in the previous classes, we have studied that heat added at constant pressure leads to enthalpy change, which is increase in enthalpy right now. So for an ideal gas, you'll have TQ equals to DH, which is equal to CP dt. All right, which is equal to CP dt. All right. Now, one thing I might have mentioned somewhere, I might have mentioned small h, and somewhere I might have mentioned capital H. Both are enthalpy, and wherever I'll be using small h, that is basically enthalpy per kg. All right, that is basically enthalpy per kg. It may be possible that I might have used capital H for enthalpy per kg, but it's actually small h which is used for enthalpy per kg. All right, so keep that in mind. So whenever you are having water, you add heat to it and you convert it into steam. So let's say enthalpy of water is H1, steam added is, heat added is Q, and steam comes out at H2. All right. So although we have not dealt with energy balance, but we have already discussed the equations involved in energy balance and somewhere in process calculations in the beginning, right? So from there, you can understand that for energy balance, we have energy in minus energy out minus, plus energy generated minus energy consumed is equal to energy stored. All right, that is there. Now, if we take this as our control volume, all right, this as our control volume, then water is coming in with an energy of H1. So that therefore E in is equal to H1. All right. Water is going out with the energy of H2. So you'll have minus H2. No generation, no conservation, no storage at steady state. And also an input heat of Q is being added over here. So Q is equal to, so when we add all this, we'll get 0. So you get from here, Q is equal to H2 minus H1. Right? Q is equal to H2 minus H1. Okay. So heat added is used to convert the water to steam. All right. So basically, it is given by the difference between the enthalpies of the final and the initial state. All right, final and the initial state. It gives you heat added. Let's say if we are turning steam, if we are moving steam to water, we are condensing steam to form water. So in that case, it would lose some heat. It would lose some heat. All right, then also the same equation would hold true. All right, then also the same equation would hold true, but this time because the directions have changed. Otherwise, the equation is going to be the same. All right, Q is equal to H2 minus H1. All right, where H2 is the larger heat and H1 is the smaller enthalpy. Okay. So this is a TH diagram, temperature versus enthalpy diagram for steam formation. This you might have started somewhere around class 9th or 10th about this diagram. So basically, this diagram represents how we have changed the temperature, how we have increased the temperature and changed matter from its solid state to its gaseous state. All right. So from this state, P to U, how has this water actually, water has come from its solid, liquid, and gaseous state. All right. So let's say we start from a particular temperature. All right. Let's take it somewhere around minus 10 degrees Celsius. All right. Somewhere like this. So it starts with ice at minus 10 degrees Celsius. You heat it. So when you heat it, its temperature would increase linearly with an increase in enthalpy. All right. Its temperature is going to increase linearly with an increase in enthalpy. Then between Q and R, Q is the state where this becomes saturated solid. All right, saturated solid. Now, if you heat it further, it is going to change its state. All right. And when we talk about R, R is going to be a saturated liquid. Okay, saturated liquid. Okay, saturated liquid over here, it's actually from the melting side. All right, from the melting side. So it's cold saturated. Okay, so between Q and R, the heat that is supplied, it is not exactly the heat that is used to increase temperature. Instead, it is used for phase change. So this heat is known as latent heat. All right. And over here, you are melting ice. Therefore, this is going to be latent heat for ice. Okay. Then from R to S, it is again in the liquid state. And you are increasing the temperature, and with that the enthalpy is also increasing linearly, right? Then it comes here at point S, where it is again saturated liquid, but this time if you increase the temperature, it is sorry, if you add more heat, then it would move on to a different state. All right, so over here it moves, and then from S to T, here T is saturated vapor. Okay, so from S to T, again the same logic. The temperature would not, the heat that is supplied, it would not lead to temperature change. Instead, it would lead to phase change. All right, and finally after T again, its temperature would increase, and over here the steam is known as superheated steam. Okay, over here the steam is known as superheated steam. So this is the TH diagram for ice melting to form steam, superheated steam. All right. So now, whenever heat is supplied, so heat supplied is basically of two types. First is sensible heat. Sensible heat leads to temperature change, as we saw in this graph, from P to Q, from R to S, and from T to U. The heat that is supplied, it is actually changing the temperature. All right, it is changing the temperature. So this kind of heat is known as sensible heat. All right, this heat is sensible heat. So it is numerically given by mCp delta T or mCp dt. All right. Then latent heat, which causes phase change. All right. So it is either mentioned by L, or even at times, for example, latent heat of ice, it is mentioned by H fusion. All right. And over here it is known as H vaporization, latent heat for phase change from liquid to vapor, it is H VAP. It is represented like this as well. All right, so over here I've just given it as L, so the numerical formula for this is M into L. All right, so this is specific latent heat. Specific latent heat, even these two, HFUS and H vape, that is specific latent heat. We'll multiply this to give you the overall heat. All right, the total heat that has been transferred. So this heat, it causes phase change. So for example, Q to R, S to T. Over here in Q to R, it is moving from solid phase to liquid phase. In S to T, it is moving from liquid phase to gaseous phase. So that is there. All right. So this is this has to be kept in mind. Okay. Some important terms that you have to keep in mind: saturated liquid at is basically liquid at its saturation. If you add more energy to this, it would lead to phase change. All right. Then saturated steam is vapor at its saturation. Extracting more energy from this vapor would lead to phase change. And extracting, that is taking away energy. And superheated steam is basically adding more energy to saturated steam. This would lead to some sensible heat being transferred to it, which would increase its temperature. So this steam that you get, it is the superheated steam. All right. So from liquid to saturated liquid, you have sensible heat that is supplied. All right. Then whatever the heat is supplied, that becomes latent heat until the state becomes saturated steam. All right. And after that, again, from saturated steam to superheated steam, whatever heat is transferred, that is the sensible heat. All right. So keep this in mind. Then we come to something called steam tables. So steam tables basically gives you data like specific volume, internal energy, enthalpy, entropy of steam or of saturated liquid, saturated vapor, and superheated vapor. So it gives you data about this, and this at a particular pressure and temperature. So for example, if I have to find the data for saturated liquid at 20 kilopascal, So it will give you the saturation temperature, that is 333.21 Kelvin. It will give us the specific volume of saturated liquid, specific volume of saturated vapor, saturated in internal energy of saturated liquid, internal energy of saturated vapor, enthalpy of saturated liquid as well as vapor, and finally entropy of saturated liquid and vapor. All these are specific volume, specific internal energy, specific enthalpy, specific entropy. So this is basically per kg, volume per kg, internal energy per kg, enthalpy per kg, entropy per kg. All right. And then we have superheated steam tables. So once saturation is achieved at a particular pressure, so the temperature is 318.96. So at that particular temperature, saturation has been achieved. Now, when you increase the temperature further, it is actually going to be superheated. It is actually going to be superheated. So accordingly, the data changes. So those data you can have over here. All right. Then we come to a very important thermodynamic property, which is quality. Quality is very important when we talk about steam. All right. So when the state of water is such that, see, what happens is that if we come back to this diagram, so over here, if it starts with a solid state, it would increase its temperature. So it will come to its freezing point. Over there, it would change its phase for some time. The heat added would lead to phase change. So that particular time, the solid and the liquid both are in equilibrium with each other. All right, both are in equilibrium with each other. Then further, if I add more heat, then from here it would increase its temperature till the boiling point of liquid. There the liquid becomes saturated. Now you add more heat, so it will use that heat to change its phase, and finally it would go to the superheated state. So in this part, that is Q to R and S to T, there is not just one state, there are two states. For example, in Q to R, there is solid as well as liquid. There is a mixture of these two states. Similarly, in ST, there is liquid as well as vapor. All right, liquid as well as vapor. So both the states are present in solid, in S to T and Q to R. All right. So in order to deal with this part, liquid vapor, we have a term called quality. Now we'll come to it. So quality is basically when the state of water is such that it lies in the vapor liquid equilibrium region. Vapor liquid equilibrium as in S to T. So over here, between saturated liquid S and saturated vapor T. All right. Then there is a fraction of the mixture, that is liquid water, and the rest is steam. Right. There is liquid plus vapor in this state. Right. Some fraction of this entire thing, mixture, it's liquid, and the rest of it is vapor. So the mass fraction of steam as in vapor, in the mixture of steam and water, vapor and liquid. Okay. So in a mixture of vapor and liquid is called the quality of the steam. All right. It is known as the quality of steam. And then if Ms is the mass of steam and in the mixture, and Mw is the mass of water in the mixture, then since X quality is the mass fraction of steam, so therefore X is going to be mass fraction of steam, mass of steam upon total mass of liquid as well as vapor. All right. So this is X. All right. So this is basically your quality. Quality is very important for evaluating a lot of characteristics, a lot of thermodynamic properties, heat capacity, heat, enthalpy, internal energy, specific volume. All these things have to be kept in mind while we are calculating this. Okay. So this quality is very helpful in calculating, in gathering information about this region, vapor liquid. All right, so over here in this state where there is vapor as well as liquid, this quality gives us information about various variables that are involved, various variable values that are there. All right. So when we physically explain quality, so if this is saturated liquid and this is saturated steam, then quality, uh, basically a mixture of liquid plus vapor. All right, both would be found somewhere here. All right, in between these two. All right, so in this particular curve, if you see, you can find this somewhere here, 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 here. So you can get quality everywhere. All right, here the quality would be different, here the quality would be different. So the closer this state of yours, the closer it is to saturated liquid, it is going to have more of liquid with it. So in that case, the quality would be closer to 0. All right, quality would be closer to 0. And as it goes towards saturated vapor, the quality would go close to 1. So if quality is 0, then it is at saturated liquid state. And if it is 1, then it is at saturated vapor. So in between, the quality is going to be from 0 to 1. All right. So basically, if you know that steam mixture over here, it has quality X, then how can we find the enthalpy? Okay, so basically it is a mixture of some amount of saturated liquid and some amount of saturated vapor or saturated steam. All right, so let's say MW is the amount of saturated liquid over here. MW is the amount of saturated liquid over here, and Mg or Ms is the amount of saturated vapor over here. Then in that case, the enthalpy, the total enthalpy is going to be Mw into Hw, that is enthalpy of liquid, plus Ms into Hs or Hg, which is enthalpy of vapor, right? And let's say H is the small h is the specific enthalpy. So it is going to be the total mass into the specific enthalpy. And total mass is nothing but Ms plus Mw. Therefore, we'll finally get Ms plus Mw into H is equal to Mw into Hw plus Ms into Hg. All right. So from here, you'll get H is equal to Mw by Ms plus Mw into Hw plus Ms upon Ms plus Mw into Hg. Remember, wherever I have written Ms, it means mass of vapor, and Mw means mass of liquid. You might also see that we write it as Mv or Ml, something like that. All right, so it's the same thing. Okay, don't get confused with the way it is denoted. All right, so this is there. So from here, we finally get, now we know that Ms upon Ms plus Mw is X. So from here, we'll get H is equal to X into Hg, because this part is your X. And therefore, Mw upon Ms plus Mw is going to be 1 minus X into Hw. Hw, we generally don't write it as Hw, it's either Hf or Hl. All right, so keep that in mind. Okay, so keep this in mind that whenever we have any point over here between saturated liquid and vapor, so over here, let's say this is your saturated liquid, and over here, this is your saturated vapor. So in between, if you take any point, all right, so if this is the enthalpy of HL is the enthalpy of saturated liquid and Hg is the enthalpy of saturated vapor, then the enthalpy over here, it would be between HL and Hg. Same applies for other properties. For example, internal energy, specific internal energy, specific volume, all right, specific entropy. Okay, all of these are going to be between liquid and vapor state. All right. So in order to calculate them, we are going to use similar methods. Okay. So H, just like we derived over here, 1 minus x into HF plus x into HG. Similarly, for internal energy, volume, specific volume, and specific entropy, we are going to use the same formulas. All right. So keeping all these things in mind, let's move on to example number 1. We have steam at 25 kilopascal and 338 Kelvin, which has enthalpy 1000 kilojoule per kg. This is the specific enthalpy. All right, this is the specific enthalpy. So calculate entropy, internal energy, density, and heat added per kg. All right, so if we go back to the steam tables, so over here, my pressure in the question is 25 kilopascal. So let's move on to 25 kilopascal. So at 25 kilopascal, the saturation temperature is around 338 Kelvin, right? So that means over here, this is either at saturation or it is somewhere here, right? It is somewhere around this line. Okay, so how to get whether steam is at saturated state S or is it at T or is it between S and T? So for that, what we do, we use steam tables. So we have been given enthalpy. Enthalpy has been given as 1000 kilojoule per kg, specific enthalpy. So we'll check. So at 25 kilopascal and 338 Kelvin, the enthalpy of liquid, saturated liquid is 271.93. And the enthalpy of saturated vapor is 2618.2. All right. The enthalpy that is of steam, that is actually between these, right? So that means that it is over here, somewhere between S and T. All right, somewhere between S and T. So once we have got that it is somewhere between S and T, therefore we know that S is going, therefore we know that enthalpy is going to be 1 minus x into HF or HL plus x into Hg. Similarly, S is going to be 1 minus x into SF plus x into Sg and so on. All right, this is what we know. Okay, so since we have been given 1000 kilojoule per kg and we have been given information like 25 kilopascal and 338 Kelvin. So with this information, we'll go to the steam tables, and from steam tables, we'll calculate individual data. We'll get the individual data. So at P is equal to 25 kilopascal and at T equals to 338 Kelvin, we are going to go to the steam tables and get the values. All right, so we'll get specific volume of saturated liquid is 1.02 into 10 to the power minus 3 meter cube per kg. Okay. Similarly, VG. So we'll have a VG from the steam tables. It is 6.204 meter cube per kg. Then UL over here is 271.9 kilojoule per kg. And UG is 2463.1 kilojoule per kg. So this way, from the steam tables, we can calculate, we can get the values of VL, VG, UL, UG, HL, HG, and SL and SG, where V is the specific volume, U is specific internal energy, H is specific enthalpy, and S is specific entropy. Now, we are going to use the formula that we derived. H is equal to 1 minus x into HF or HL plus x into Hg. we have H equals to 1000. We have HL from steam tables. We have Hg from steam tables. So using all these values, we can get X. So X we'll get as 0.31. All right. X we'll get as 0.3. This is the quality. All right. You might also see that this is called as dryness fraction in certain books. So it's the same thing. All right. So X is equal to 0.31. Once we get X, then we can get anything, entropy, internal energy, specific volume. So we have been asked for entropy. So specific entropy is going to be 1 minus X into into SL plus X into SG. So X is 0.31, SL and SG we already have from the steam tables. So this is going to be 3.046 kilojoule per kg Kelvin. All right. Next, they have asked us to calculate the internal energy. So internal energy, again, same way, 1 minus X into UL plus X into UG. So that is going to be UL and UG we already have from the steam tables. So this we'll get as 951.172 kilojoule per kg Kelvin. Not kg Kelvin, only kg. Kilojoule per kg. Okay. Then the third, they have asked us to calculate density, right? So density, as you know, we have discussed in one of the videos that density can be written as 1 upon specific volume, right? Because specific volume is volume per kg and density is mass per volume. So it's basically 1 upon specific volume gives you the density. All right. So we have to calculate the specific volume for this. So specific volume that we get, that is VL into 1 minus X plus X into VG. So the specific volume comes as 1.924 meter cube per kg. Therefore, density is going to be 1 upon the specific volume, that is 0.51976 kg per meter cube. That is density. Then in the fourth question, they are saying that calculate the heat added per kg of steam to increase its temperature to 500 Kelvin, keeping pressure constant. So since we have to keep the pressure constant, therefore heat added is going to be equal to the difference in the enthalpies. So we already know the enthalpy over here is 1000 kilojoule per kg. Then we need to calculate the enthalpy at 500 Kelvin. So 25 kilopascal, the final state that we have to keep. Final state that we have to keep is basically 25 kilopascal and 500 Kelvin, right? All right, 25 kilopascal and 500 Kelvin. All right, so in that case, from the steam tables, we can get the enthalpy. So the specific enthalpy for this condition, 25 kilopascal and 500 Kelvin. The specific enthalpy is 2928.4 kilojoule per kg. All right, somewhere around this. This is the specific enthalpy. Okay, now the heat transfer. The heat transferred is basically enthalpy in the final state minus enthalpy in the initial state. So enthalpy in the final state is 2928.4. Enthalpy in the initial state is 1000. All right, so this becomes 1928.4 kilojoule per kg. This is the heat that has to be added to increase the temperature at constant pressure. All right, this is the heat that has to be added to increase the temperature. increase the temperature to 500 Kelvin, keeping the pressure constant. All right. So hope you could understand how to solve this problem. First, we have to get all the data. First, we have to basically identify the pressure and temperature. And using that, we have to get the data from steam tables. Once we have the data from steam tables, then we have to find the quality if there is any requirement for quality. Once we have the quality, then we can find the respective entropy, internal energy, internal energy, maybe enthalpy if you want, and specific volume at that particular state. And finally, after that, you can get the values. All right. In order to calculate heat transferred for such cases, you simply subtract the final enthalpy and initial enthalpy to get the heat that is added. Okay. So it's quite simple. With this, we move on to example number 2. Determine the state and find the entropy of 1 kg of steam at a pressure of 12 bar and a temperature of 250 degrees Celsius. Take specific heat of steam at the state as 2.1 kilojoule per kg Kelvin. If we reduce the heat of steam, if we reduce the temperature at constant pressure, at what temperature would steam would have equal mass of liquid and vapor? Would have equal mass in the liquid and vapor phase. What would be the entropy change during this state transition? So let's understand this question. So basically, initially we have 12 bar, pressure equals to 12 bar, which is 1200 kilopascal. All right, and temperature we have as 250 degrees Celsius. All right, so we have pressure, we have temperature. Now we can get the different properties of steam, right? We can get different properties of steam. Now remember, at each pressure, there is a saturation temperature, right? A saturation temperature, which is basically the boiling point of any of liquid, right? So for P, the saturation temperature is 188 degrees Celsius. For 1200 kilopascal, the saturation temperature is 188 degrees Celsius. And this temperature is greater than the saturation temperature, right? So if the temperature is greater than the saturation temperature, then we all know it is superheated steam. It is superheated steam. So if it is superheated steam, then we have to go to the superheated steam tables and find the values accordingly. All right. So in the superheated steam tables, we'll find 1200 kilopascal. It is actually not given as in terms of kilopascal in most steam tables. It is given in megapascals. So 1200 kilopascal is basically 1.2 megapascal, right? So you'll get 1.2 megapascal over there. And on the basis of that, you can calculate the pressure and temperature. All right. Sorry, on the basis of that, you can get all the other properties. So the specific volume is 0.19241 meter cube per kg at this state. All right. Then specific internal energy is 2704.7 kilojoule kilojoule per kg. Then enthalpy, specific enthalpy of the superheated steam is 2935.6 kilojoule per kg. And finally, you have entropy, which is 6.8313 kilojoule per kg Kelvin. All right. So if you see over here, they have asked you to calculate the entropy of 1 kg of steam. So this is the entropy. All right, at this state. Okay, so this is what they asked you to calculate. All right, and they have also asked you to determine the state, so that is superheated steam. All right, superheated steam. Okay, once we are done, then we have to reduce its temperature. So basically, if we have the temperature versus enthalpy diagram, then this was the diagram, right? So this is going to be the boiling point. This is the freezing point, right? Or the melting point, right? So over here, you have saturated vapor, and this is somewhere at the steam, superheated steam over here. So this is the saturated liquid. Here you have saturated vapor, and here you have superheated steam. So let's say we are at superheated state. So here there is 250 degrees Celsius. From here, you have to come to a point where there is a mixture of vapor and liquid. So mixture of vapor and liquid is found only over here, right? Somewhere between this point S and T, right? Somewhere between S and T. Only here you can find, a mixture of liquid and vapor. All right. So if that is the case, then you have to reduce the temperature from its boiling, from 250 degrees Celsius to the boiling point, which is the saturation temperature, right? So therefore, the temperature at this state, they have asked you to calculate temperature. So that temperature is basically going to be the saturation temperature. So that is 188 degree Celsius. All right. So keep this thing in mind. Okay. Once you have got this, then you can also get the values of saturated entropy of saturated liquid, and entropy of saturated vapor. All right. So these values you can get from steam table. So the entropy of saturated liquid is 2.2159 kilojoule per kg Kelvin. And entropy of saturated vapor is 6.5217 kilojoule per kg Kelvin. All right. And then they have said that there is equal mass of liquid and vapor. So that means that MW is equal to MS. Therefore, X, which is MS upon MW plus MS, is going to be 0.5, right? Equal mass. Therefore, when you calculate the entropy is going to be 1 minus X into SL plus X into SG, that is 1 minus 0.5, that is 0.5 into SL plus 0.5 into SG, that is SL plus SG into 0.5. Now, SL and SG we already have from the steam tables. Therefore, the entropy at this state you will get as 4.3688 kilojoule per kg Kelvin. All right, this is the entropy. So entropy change is going to be entropy, and basically the difference in entropy, that is 6.8313 minus 4.3688. So that is going to be 2.4625 kilojoule per kg Kelvin. So this much entropy has decreased. This much entropy has to be decreased in order to get it to this kind of a state. All right. So hope you're clear with this problem. Then we move on to example number 3. Find the internal energy of 1 kg of steam at 20 bar when it is superheated and its temperature is 400 degrees Celsius. So over here you can find the state using steam tables. You have to go to the superheated steam tables. You have to find 20 bar, that is 2000 kilopascal, which is 2 megapascal. and you have to find 400 degrees Celsius. So over here, you'll find internal energy from the steam table. That is going to be equal to, for the superheat part, it is going to be 2945.9 kilojoule per kg. All right, then it is wet and its dryness being 0.9. So dryness fraction, quality, same thing. So this is basically X. They have given you X equals to 0.9. So 20 bar, at 20 bar, the saturation temperature is whatever the saturation temperature might be at 20 bar. You can get that from the steam table. And similarly, you can get values for internal energy of liquid state, internal energy of vapor state from the steam table. And then you only have to calculate U is equal to 1 minus X into UL plus X into UG. All right. So this is going to be 1 minus 0.9, that is 0.1 into UL plus 0.9 into UG. So at 20 bar at saturation, the internal energy of saturated liquid, it is 906.12. This value again we have got from the steam table. And UG is 2599.1 kilojoule per kg. So you'll get this value equal to 2429.802 kilojoule per kg. So that is that. All right. If suppose I ask you that what is the mass of liquid part and what is the mass of the vapor part, so again you can calculate that using dryness. So X is equal to ms upon ms plus mw. So we have 1 kg in total. So ms upon 1 is equal to 0.9. Therefore steam, that is the vapor is 0.9 kg and liquid is 0.1 kg. All right, so something like that. So there are a lot of ways you can use to calculate enthalpy, internal energy, and all these things. All right. So then we move on to example number 4. A vessel. This is a interesting kind of an example. A vessel having a capacity of 0.05 meter cube containing a mixture of saturated water and saturated steam at a temperature of 245 degrees Celsius. Now over here, they have actually given us the saturated temperature. So at this saturation temperature, we have to find the pressure. All right. So the first part is very easy. We have to find at T equals to T saturation, which is 245 degrees Celsius. We have to find P. So pressure over here in this case, when 245 degrees Celsius is the temperature, then pressure is the 3651.2 kilopascal. All right, which is also 36.5 bar, approximately 36.5 bar. All right, so this you've got. Then we move on to the second part. So before we solve for other parts, let's get the values from the steam tables. So from steam tables, we'll get values for a specific volume of saturated liquid, specific volume of saturated vapor, internal energy of saturated liquid, internal energy of saturated vapor, enthalpy of saturated liquid, enthalpy of saturated vapor, and entropy of saturated liquid, entropy of saturated vapor. All right, so we'll get these values from the steam tables. So this is 0.00124 meter cube per kg. All right. So we have got from the steam tables values of specific volume, specific internal energy, enthalpy, and entropy. of saturated liquid and saturated vapor. Once we have got all these things, then we'll move on to the rest of the question. They are saying that the mass of the liquid present is 10 kg. So since mass of the liquid is known, mass of the liquid MF is equal to 10 kg. Therefore, the total volume of liquid present is equal to mass of the liquid into its specific volume, right? So that is 10 into 0.00124 meter cube per kg, right? So that is 0.0124 meter cube. That is volume of the liquid present. All right, that is the volume of liquid present. Total volume of the vessel is 0.05. So total volume is basically volume of the liquid plus volume of vapor present. So from here, volume of vapor present is 0.05 total volume minus volume of the liquid, that is 0.0124. All right. So 0.05 minus 0.0124 is 0.0376 meter cube. This is the volume that is occupied by the vapor. Okay. So with all these things, we move on to part number 2. You have to find the mass of the mixture. So mass of the mixture is basically mass of liquid plus mass of vapor. So mass of liquid, we already have 10 kg. To find the mass of vapor, we have the volume of vapor and we have the specific volume of vapor. So mass of vapor is basically volume of vapor upon specific volume of vapor. So that is 0.0376 meter cube upon specific volume, that is 0.054656. 0.054656. All right, so that is 0.688. This is in meter cube and this is in meter cube per kg. So this overall becomes 0.688 kg. All right, 0.688 kg. So the total mass becomes 10, that is mass of liquid, plus 0.688, which is 10.688 kg. All right. Then we have to calculate the specific volume. So specific volume, you can calculate it in two manners. First, what you can do is you have mass of liquid, you have mass of vapor. So what you can do is you can calculate quality, that is mass of vapor upon vapor plus liquid, right? So that is 0.688 upon 10.688, right? So the quality, it would come equal to 0.0644. All right, that is quality. All right, then from here, conventionally specific volume is equal to, you all have Vg, Vl. So from here you can get Vg into X plus Vl or Vf into 1 minus X. So this gives you the specific volume as 0.004678 meter cube per kg. Second thing what you can do is, you already have the total volume, right? 0.05 meter cube. And you have the total mass, 10.688. So the specific volume is basically volume per unit mass. So that is 0.05 upon 10.688, correct? So this will also give you the specific volume, which will give you the same answer, 0.004678 meter cube per kg. So you can get both. You can get it both ways. All right. So you don't have to worry about that. All right. Then next thing, we have to calculate the specific enthalpy. So we are again going to use the same formula. H is equal to HF into 1 minus X plus Hg into X. So when we solve, you'll get the specific enthalpy as 1173.6 kilojoule per kg. Quality you have already calculated. How to calculate? We just discussed. All right. Then the next thing that you have to calculate is the specific entropy. So specific entropy is equal to specific entropy, again same way, SF into 1 minus X plus Sg into X. So that is going to be equal to 2.964 kilojoule per kg Kelvin. Okay, and finally you have to find the specific internal energy. So again, to calculate specific internal energy, you can use two methods. One method is the conventional method, UF into 1 minus X plus UG into X. So when you solve, you will get it as 1156.45 kilojoule per kg. All right. Or what you can do is, since we know that H is equal to U plus PV, therefore, where V is the specific volume here and P is the pressure. Therefore, you can get U is equal to specific enthalpy minus pressure into specific volume. The specific enthalpy you've already calculated, 1173.6. Specific volume you've already calculated, 0.004678. And pressure you have 3651.2 kilopascal. So this is going to be 1173.6 minus pressure, that is 3651.2 into specific volume, which is 0.00467. 0.00467. All right. About the units, the pressure is in kilopascal. The volume, specific volume, is in meter cube per kg. So kilopascal meter cube is basically kilojoule. So this becomes kilojoule per kg. All right. So units are all balanced. Therefore, from here you will get internal energy as 1156.52 kilojoule per kg. So if you see, they're approximately same. So you can calculate internal energy in both the manners. All right. So hope you people could understand what we did in this problem. All right. How we got the volume of vapor, how we got the volume of the specific volume, and again another way of calculating internal energy. So these all concepts we learned through this problem. All right. So hope you people are clear with this problem. This was a very important problem. So make sure that you're clear with this problem. All right. Then we move on to the final example for our lecture. Steam undergoes isentropic expansion. Isentropic expansion means entropy is constant. All right. So it undergoes an isentropic expansion in a turbine from 5000 kilopascal and 673 Kelvin. And they have given the entropy as 6.65 kilojoule per kg Kelvin to 150 kilopascal, where the entropy of saturated liquid is this and entropy of saturated vapor is this. The exit condition of the steam is, we don't know. All right. So go ahead, pause the video and try to solve this problem yourself. So let's see how to solve this problem. Okay. So when we talk about the initial state, let's call it 1. Let's call this state as 1. So when it was at state 1, then entropy is given to be 6.65 kilojoule per kg. 6.65 kilojoule per kg. All right. And in the final state, since it is undergoing the isentropic expansion. All right. So let's call the final state as state number 2. So in the final state as well, the entropy is going to be the same as state 1 because it's isentropic in nature. So it's going to be 6.65 kilojoule per kg Kelvin. Now, just have a look at the two entropies, the entropy of saturated liquid and vapor. So if you see clearly, S2 lies between these two, right? S2 lies between these two. Therefore, it is going to be either, it is going to be between saturated liquid and saturated vapor state. Hence, option A and option C are already incorrect. All right, now we have to see that which one among these two is true. So now there is one trick that you can follow for this particular question. See, we are seeing S2, that is 6.65. Now, if you clearly see in this problem, it is 6.65, it is closer to this, that is entropy of saturated vapor. That means in this line between S and T, where T is saturated liquid, saturated vapor and S is saturated liquid, in this line, the entropy lies somewhere here. And here it is closer, the dryness fraction is closer to 1, right? Here it is closer to 1. So therefore, the dryness fraction, quality, it's actually going to be around 0.9. So using that trick, you can definitely say that B is the correct answer. All right. So remember this thing, that if the enthalpy, entropy, internal energy, if it is closer to vapor, then X is going to be closer to 1. And if it is closer to the liquid state, then X is going to be closer to 0. So you are going to see over here as well in the previous problems that we did. So for example, let's take this problem. So here we found X as 0.0644. The quality was closer to 0, right? So therefore, all the properties that we found, a specific volume, it was closer to that of liquid. Similarly, enthalpy, it was closer to the enthalpy of liquid, right? Then entropy, it was closer to the entropy of liquid, 2.7476, and over here it was 2.964, right? So, and similarly internal energy, 1156.45, and over here 1056.9. So it is closer to liquid. Why? Because X is closer to 0. So remember, if a property is closer to the liquid value, then X is going to be closer to 0. And if a property is going to be closer to the vapor value, then it is going to be 1. So I'll write it down. If property is closer to saturated liquid value, then X is going to be closer to 0. And if property is closer to a saturated vapor value, then in that case, X is going to be closer to 1. Okay, so keep this trick in mind. This is a very important trick which can be used to solve steam related problems. Okay, so by this method you have got the answer as 0.9, but let's solve it conventionally. So we have entropy of final state as 6.65, and you have already been given Sg and Sl. So we know that S2 is going to be 1 minus X into Sf plus into Sl plus X into Sg. All right. So from here you get X as S2 minus Sl whole upon Sg minus Sl. All right. So S2 is 6.65, SL is 1.4336, SG is 7.2234. So when you put the value, you will get X is equal to 0.9, which is again option number B. All right. So this problem really did not require too much of uh, too much of uh, exhaustion. Right, it was quite easy. You could directly apply some of your logic and get the answer. All right, so this was about steam. We have discussed different properties of steam, how to calculate different properties of steam. We've discussed about steam tables, superheated and saturated steam tables, and then we discussed certain problems on steam. Hope this lecture was clear.